And we're in business. Okay. Now, can you see my screen? You should only see a question and then up my whiteboard, okay, with the number 30 on. Can you see that? Those of you that are tuned in, can you see that? My screen that I'm sharing on Teams? A question with a part of a box and, of course, my whiteboard. In short terms, can you see what I'm sharing on Team? Okay, thank you. Thank you, thank you. Okay, now today is going to be a short session. Okay, before I begin, if you have any questions, just at any point stop me and ask the question. Otherwise, if you have any questions regarding your work, you can just email it to me if you can't type it there. And at any point, stop me, ask a question. If you need anything else, just email me the question and I will look through it for you. Okay, now let's just start. So I'm not going to waste your time any longer. This is just question 30. You guys don't need to worry about the question numbers, okay? You need to worry about the actual question. Okay, now, this question just says the electric field in the region of space shown. Okay, so we have this region of space here, okay? This cube, okay? And this electric field is given by, the electric field is given by this. Remember, an electric field is still a vector and it's given by this formula. Right? It's I hat and 2y j hat. This is the electric field that they give us, okay? And it's in newtons per coulomb as always. Well, not always. It's not always measured in newtons per coulomb. Yes. Now that's the electric field that they gave us. And y is in centimeters, or excuse me, is in meters, they tell us. So we've been given an electric field in some region of a space, and the electric field is described by this. Let me just check here. Someone is trying to log. Admit this person. Okay. So we have an electric field going through space, and in this space there is this cube. Okay. Now the question is, what is the magnitude of the electric flux through the top surface of the cube? What is the magnitude of the electric flux through the top surface of this cube? Okay, now I'm going to scroll a bit up. We want the electric flux. Remember, the electric field is described by the equation I just wrote down. They want the electric field through the top surface of this cube. Okay, through the top surface of this cube. There's the cube. Okay, I'm not going to redraw it. You can look just at it there. It starts at x is equal to 2 meters, and then it ends 3 meters later, so at x equals to 5. So the box has uh, 3 meters in length along the x-axis, 3 meters in length along the y-axis, and 3 meters in height. So this is the box. They want the electric field going through the top of this box. Now, we've been given that the electric field is described by this formula. E is equal to 8y plus 2, 8I hat plus 2y j hat. Okay, this is the electric field. Okay, now what is the electric field going through the top of the surface? Okay, what is the electric field going through the top of the surface? Okay, the top of the surface in terms of y. Where's the top of the surface in terms of y? Okay, here we have x in that direction. I don't know if you can see it. And then y-axis is going upwards. Okay, so where exactly on the y-axis does this electric field go through? At what position? Can anyone tell me at what position on the y-axis is the top surface? Anyone in the comments? Oh, not in the comments. In Teams, can you please tell me at what value of y is the top surface? Remember, this cube has two side surfaces, a front and a back surface, and then a top and a bottom surface. Okay. At what value of y is the top surface located? Anyone hazard a guess? Anyone brave to type it in the comments? At what value of y is the top surface? Okay. Look at this box. At what value of y will you start entering the top surface? Okay, let me tell you rather than the top surface, and just for the record, you're going to have a lot of these questions, so you need to know how the top face. Okay, we're looking at the top face. The top face is at y equals to 3. So that's where the top face is. Okay, so at y equals to 3. So the electric field, that means the electric field going through the top surface is equal to, remember that electric field is the generalized formula. It describes the electric field anywhere, everywhere in the region of space there. Let me just look. And then Lolita, thank you. That is correct. 3 meters. Taviso as well, 3 meters. So the top surface is at 3 meters. So we're going to plug in y is equal to 3. The j hat. That means our formula now, just for going for the electric field going through the top surface, then is equal to 8 I hat plus 6 j hat, and that is the electric field going only through the top surface. Okay, only through the top surface. So that's the electric field going through the top surface. Of course, it's in newtons per coulomb. Now they want to know what's the magnitude of the flux going through there. Remember, an electric field going through a certain area creates a flux. They want to know what's the flux through the top surface. Okay. Now, in order for us to create electric flux, what do we need? The flux through any surface, we need two things. Okay. If we want to calculate electric flux, and remember, this is the formula for electric flux, or the symbol rather for electric flux, it's equal to the electric field dotted with the area vector. Okay, the electric field dotted with the area vector, that is the electric flux. Now we already know what the electric field is going through the top surface. It's that the electric field going through the top surface, we know it. Let's write it down again. The electric field going through the top surface is equal to 8 I hat plus 6 j hat. That's the electric field going through the top surface. What is the area of the top surface? How do we work out that area? Okay, it is 3 by 3. So it is 3 multiplied by 3. That's equal to 9. Now that surface, okay, remember this is not just an area, it's an area vector. Okay, an area vector, meaning it will have an I hat, a j hat, or a k hat. Okay, now the area vector is always, and you should have learned this by now, is always perpendicular to the area itself. Okay, now if we were to look at that box there, okay, with the top surface, okay, the area vector is going to point in which direction? Is the area vector going to point in x, y? Okay, let me just admit the student. Okay. We used a very small diamond emitter. It was about 92. Aluluto, yes, thank you. Okay, now In which direction is the area vector? Let me just draw the box here. And this is going to be a terrible drawing. Remember, we are now looking only, terrible, let me redraw that. Try to make them parallel. Okay, that one as well. There we go. Okay, so we are looking at this box, right? Okay. Specifically, we're looking at this surface here, okay, the top surface, okay. Now we found out what the area is, okay. Now the area vector is always perpendicular to that area. Now there are two directions which is perpendicular to that area, one going down and one going up, okay. Now if we were to choose going down, it will be negative, but in this case, we're just working with positive values. So we are just looking at the area vector pointing from that area. In this case, the area we're looking at it downwards, so the area vector would be going upwards in the direction of y. Now, any value going in the direction of y is an j hat component. Excuse me. Okay? We are looking at this. This would be the area vector. That's the area vector. Okay, for this area. This one's area vector would point that direction. The one at the bottom would point down. That one on the left would point in that direction. The one in the front would point in this direction. Those are all area vectors, okay? Now the area vector for the top surface is pointing in the j hat direction, okay? That's why I'm writing 9 j hat, and I'm going to write it again, don't worry. So the area vector is 9 j hat. So let's calculate the flux as we've been asked to. Electric flux is equal to the dot product of the electric field, with the area vector. Okay, now that would then be 8 I hat plus 6 j hat dotted with 9 j hat. And there we have the electric flux. Now, of course, you still need to calculate all of this out. So this will then be 8 multiplied by 0 because there's no a 0 I hat component plus 6 times 9. That will be 0, and that will be 6 times 9 is 6 times 10 is 60, minus 6 is 54. So the answer would be 54 meters squared per coulomb. Okay, so that is the electric field, 54 meters squared per coulomb, the electric flux, excuse me. Let's check if we are correct. So we've calculated the electric flux only through the top surface. Now you can calculate it for any one of these. The only difference is going to be every time is the area vector. Since this is a cube, the area for every surface will be 9, but the area vector is going to change. If let's say they asked for the surface here on the right hand side, okay, the area vector would be I hat, so it will be 54. So it will be 9 I hat, so it will be 8 times 9, and then that would be your electric flux through that surface. So this is the electric flux through that surface. You can ask a question if you need to. Don't worry. Go ahead. If there's someone who wants to ask a question, if there anyone who wants me to explain again, okay, Aluluto, you can ask a question if you have. Okay, Bandile, you guys just Go ahead. What's the question? Okay, let me see. There's something in the chat. I keep seeing attendance registers here. Okay, guys, you can go ahead and ask the question. I can't see any questions in the chat. For some reason, my chat is only showing attendance registers.
So may you please explain again?
Okay, we have a box, guys. This is a box. Okay. Oh, yes. And in the region of this box, there is an electric field. Okay, this electric field is described by the formula 8 I hat plus 2 y j hat. So this is the electric field in the region of this box, right? Okay, so we have this electric field. It's in the region of this box. Okay, so there is an electric field. Now they tell you that if you want to know specifically what the field is at a certain height, this field, let's say it's going down like this. Okay, let's say this is the electric, rather, this is not a non-uniform, it's a uniform field. So we have an electric field going down like this. Okay? Imagine those lines are parallel. Okay? It's not exactly going down like that because it has an x and a y component. So most likely it's at an angle. Okay, so we have an electric field in that region. Okay, now they want to know how much of that electric field is going through the top of this box. How much of that electric field is going through the top of that box? Okay, now they tell you that this electric field changes according to at what level of y it is at. Okay, meaning if it, let's say this is the box is at 3, right? This is the surface is at 3, this is at 0, this is at 1, let's say that's at 2. This means, according to this formula, it means the electric field is going to be different here, here, and there. At each level of y, if y changes, the electric field will have a different value. Does that make sense? Raise your hand if that makes sense to you. You guys, Aluluto and Bandile, can you just take your hands down in the comments there, please. In the From your profiles, I need to see. Now I'm actually going to test if you have questions. Okay, do you guys understand what I'm trying to say at the moment? Okay, ignore what I've said before. They understand that this electric field changes according to what position of Y you are at. Just give me a thumbs up if you understand that concept. You understand the concept. Okay, so you guys understand that the electric field changes at what uh, level of Y you're at. Okay. Now remember, this box has a height of 3 meters. Okay, so if you guys look there, in the background of that drawing, you'll see an axis there, and you'll see that it's Y in this direction. Okay, then we have Z here in this direction, if I'm not mistaken, and X in this direction. Okay, it's all in the drawing there. Okay? Now we want to know the electric field specifically just for this face here, that face there. Okay, the top surface. Okay, the top face. We want to know how much electric field is going through there, meaning how much of flux. Okay, what is the electric flux going through that surface? So what we do is, first of all, we need to determine what is flux. We know that flux is equal to electric field at that, going through that point, m- dotted with the area that it goes through. Okay, that's what flux is. Okay, think of flux as, let's say you have a hose pipe. Okay, you have a hose pipe. Okay, and you put your finger. You guys, if you've ever done that on a hot day, you put your finger on the front of the hose pipe to make it the opening narrower. That way, the water sprays out. Okay? Now, let's say your friend is there holding a hula hoop or something round. Okay, electric flux would be the amount of that water that is going through that hoop. Okay, does that make sense? Raise your hand if you understand the concept of flux. It's just the amount of something that goes through a certain area. Think of it as water. Okay, if you're spraying water and someone is holding a round shape, the amount of water that goes through the round shape, that is the flux. That is what flux is. Okay, we're just calculating how much of the electric field is going through that surface area. Okay, now we know what the flux is. Okay, and we know that we need electric field and area. Both of them must be vectors, okay? So we have electric field and area, both of them vectors. Now, let's work out what is the electric field at a certain y. The y in question is equal to 3 because we're looking only at the top surface, only at the top surface. So the y value, if we plug in 3 for the y value, we would get the electric field at the top surface. Does everyone understand that? Just by thumbs up if you understand it, or keep quiet. Okay, Tabiso, Aluto, I see you guys raising your hands. Cool, 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 cool. So now you know that the electric field, exact electric field value, we know we're looking only at the top surface, and the top surface is situated at y is equal to 3. So we plug in y is equal to 3, j hat. So the electric field then, this is now the electric field at the top surface, 6 j hat. So now we have the electric field, newtons per coulomb. So now we have the electric field at the top surface. This is the electric field that's going through the top surface, the value of electric field. We have that now. Okay. So next question then is, what is the area of that surface that the electric field is going through? What's the area? Let's work it out. The area of that top surface is, it has a length of 3 meters and a width of 3 meters. Okay, and how do we calculate the area of a square? It's just that value squared, or just 3 by 3. So if you were to calculate, if you don't understand why this area is square, okay, it has a length of 3 meters in the x direction, and it has a length of 3 meters in the z direction, meaning its area will be 3 multiplied by 3, and that is the area of this uh, the area of the top surface. But here's the problem. We don't just want the area, we want the area vector. Okay. Now an area vector is simple. Okay. It is basically the area that you calculate, and then just you take draw a perpendicular line. This is the box. Let's say this is the box area that we're looking at. We're looking at the top surface only. This, we've already calculated the area. It's 3 meters this way and 3 meters that way. So we've calculated that area value. But in order to make it a vector, we must find out this vector here. Okay. In which direction does that arrow point? An area vector in which it points is always perpendicular to the area itself. This area is in the xz plane, meaning the vector will be pointing in the y direction. Okay, and whenever something points in the y direction, it is in the j hat direction. Does that make sense? Give me a thumbs up if that makes sense. And to you, okay, it makes sense to one person. Okay, cool. Aluluto, thank you guys. So now we have both of these things, okay? We want the flux through that top surface. We have the electric field going through the top surface. Remember, the electric field going through the top surface is equal to 8 I hat plus 6 j hat dotted with the area vector, and that will have the flux. The electric field is 8 I hat plus 6 j hat dotted with 9 j hat. Okay, now you guys know when you're getting a dot product, you multiply individual I hats and individual uh, j hats. Okay, I hat here is 8. The I hat on that side is 0, so that's why we don't write it. Plus 6 j hat multiplied by 9 j hat, so it's 6 multiplied by 9, and that gives me 54. Did everyone understand it the second time around? Meter squared per coulomb. Okay, okay, so now we know how much of the electric field is going through that top surface at a certain point. So 54, let's check on this answer sheet. Let's check 54. Let's answer 54. Sorry, I keep forgetting to write Newton meter squared per coulomb. Okay, I just keep writing meter squared. Let's check. Okay, that's 34. Refuses to accept my answer now, but yes, there is 54. Doesn't allow. Okay, yes, there it is. The correct answer is 54 Newton meter squared per coulomb. Okay, let's just go now to question number 31. Remember, we are just doing 4 questions today, I think. Yes, 4. The charge of uniform density. So we have a charge. It has a uniform density of 0.3 nanocoulomb per meter squared. Okay, so we have a charge of uniform density. It's distributed over the xy plane and a charge of uniform density negative zero point 0.4 nanocoulomb per square meter is distributed over the yz plane. What is the magnitude of the resulting electric field at any point not in either of the two charged planes? Okay, so any point not in either of the two charged planes. Okay, so first of all, how do we calculate the electric field for a charged plane? How do we calculate the electric field for a charged plane? Okay, when we calculate the electric field, let's say this is a charged plane, this is a plane, okay, and it is a charge. It's basically a sheet, but it has a charge. Okay, now the way we calculate the electric field for a charged plane is equal to the electric field is equal to the charge density, the absolute value of that charge density, divided by 2 times the permittivity of free space. It's permittivity, right? Then it's permeability when you're using magnetism. Okay, so that is how you calculate the charge, the electric field due to a charge. You will do this when you do capacitors. Okay, and I'm sure you don't go into this a lot, I remember, but you should know this formula. Okay, who amongst you is seeing this formula for the very first time? Who's seeing this formula for the very first time? It's the electric field for a charged plate. Who is seeing this formula for the first time? Okay, if you're seeing this formula for the first time, let's say this is some charge, this is a plate. Okay, this is how you calculate the charge, the electric field due to that charged plate. Okay, you can lower your hands. So they want to calculate the magnitude of the electric field at any point not in either of those charge planes. Okay, so not in the charge planes, so everywhere else. Okay, so let me then get back to the actual question. So we have a plane is distributed over the xy plane. Let's draw the axis first. I want to make this x, that's y, and that's z. So we are first looking at a, the charge, a zero point 0.3 Newton charge, Newton nanocoulomb charge is distributed over the xy plane. This is the xy plane here. This is the xy plane. So this here, okay, let me rather draw it nicely. This plane here that I'm highlighting, this plane is the xy plane and it is charged. It has a charge of zero point 0.3 nanocoulomb. It's a charge plate. It is a charge of zero point 0.3 nanocoulomb. Then they ask us what is the then they or they rather tell us negative zero point 0.4 nanocoulomb is distributed over the YZ plane. This here is the YZ plane. Okay, the YZ plane. This one is the YZ plane. Okay, they want to know what is the charge, what is the electric field at a point not in either of these planes. Okay, so first of all, you need to calculate the electric field due to each of these planes. So the electric field due to the plane in the XY plane, in the XY field, the electric field due to the charge distribution in the XY plane is going to be equal to just the charge density over the XY plane divided by 2 times the permittivity of free space. So that would be zero point 0.3 times 10 to the negative 9. Remember, it's nanocoulomb per meter squared divided by 2 times the permittivity of free space is 8,854. I usually just use 8,85 and it's to the 10 to the negative 12. Okay, let me see if it cuts off there. Okay, it's still fine. That gives you an answer of 16.94, or rather very close to 16, approximately 16,94 newtons per coulomb. Remember, you're calculating electric field. Then we calculate the electric field due to the YZ plane. Okay, it is the charge density, the area charge density of the YZ plane divided by 2 times mu naught E naught. So it'll be zero point 0.4. Remember, we're taking the absolutes, so we just don't care about the sign. It's zero point 0.4 times 10 to the negative 9. 0.4 times 10 to the negative 9 over 2 times 8,854 times 10 to the negative 12. Okay, and that gives us that 16.94, excuse me, this gives us 22.59. So we have calculated the electric field due to both of these charged particles, okay? But we've calculated them individually, okay, for each individual charge, not as a unit, a singular unit. Okay, so let's determine the direction of the electric field. Right? The electric field from the xy plane, that meaning the one at the bottom, the xy plane, the electric field from the xy plane is perpendicular to the z-axis. Remember when we cross x by y, we get z, the positive z direction, it's perpendicular along the z-axis. Basically what they are saying is, let's say this, remember I just drew this, let me, we can remember, this is what I just did. We calculated the electric field for this plane, and then we calculated the electric field for this plane. Right? Now this electric field for this plane here, the xy, this is x, this is y, this is z. Okay? Remember when you find a cross product of two electric fields, this planes will point, the vector for this charge will point in that direction because it's x cross y. And then for this one, for that electric field, it will point along the x-axis in this direction. Okay, like I said earlier on with the area vectors. It's not an area vectors, but it's in the same direction. It will be in the same direction. Okay, so now we have the directions for both of those electric fields. Now, if we calculate the magnitude of the resultant field, so the net electric field, okay, we have one going up and one going along this direction. Okay, if we calculate, that's 90 degrees. Obviously, that one is going straight up, and that one is going straight along the x-axis. So, if we want to calculate the electric field, the net electric field here, E net, we use Pythagoras. Okay, Pythagoras. So E net is equal to the square root of E in the xy plane squared plus E in the yz plane squared, and you find the square root of that, and that, ladies and gentlemen, would be your E net, your net electric field. So it will be 16,94, if I remember correctly, squared plus the other one was 22,59 squared. Let me see if it is fitting. It's not. 22,59 squared. Square is not fitting in. There we go, square. And that, ladies and gentlemen, if you work it out, you get approximately about 28,24 nanocoulomb. That is the electric field, the net electric field due to these charged planes. Okay, that's the net electric field due to these charged planes. Okay, so just remember how we calculate the electric field due to a charged plane. I'm gonna go look. Okay, I just read the questions here. Okay, Cylinder Kusha said the charge density wasn't supposed to be lambda. I may have used different formula. Yes, linear charge density is lambda, area charge density is sigma, I think. And then we have the other one, we have a volume charge density as well. Okay, so here we have the electric field due to these two charged planes. Okay, it's 28, and let's check if 28 is the correct answer. Yes, it is 28. Now, that is this 32. Okay, a long conducting wire. So we have a long conducting wire. Let's see. So a long non-conducting cylinder, it has a radius of 12 centimeters. There's a charge of uniform density. So this is a cylinder. It has a charge of uniform density of 5 nanocoulomb per cubic meter and is distributed throughout its column. Okay. Now determine the magnitude of the electric field 5 centimeters from the axis of the cylinder. Okay, so first of all, let's look at, by the way, rho is volume charge density. Hmm. Let's convert, we know, first of all, 12 centimeters is 0.12 meters, okay? So the radius R is equal to 0.12 meters, okay? Then we have, I'm just converting to, then we have 5 nanocoulomb, that is the charge distribution. In this case, it is rho. It's the charge distribution, the volume charge distribution. It is 5.0 times 10 to the negative 9 coulombs per cubic meter. Okay, someone just asked. Okay, I don't agree with the comments there. In the chat, someone said we used. Are you referring to the previous formula or the formula I'm about to use? Because the previous formula we only use when it's a sheet, when it's two-dimensional. Okay, when it's a charge, when it's an area charge distribution. Let me just write down. Linear charge distribution is this. It's when it's. How can I say this? Okay, you know what linear charge distribution is. It's just the charge divided by some sort of length. Okay, that's linear charge distribution. Okay. Uh, area charge distribution is equal to a charge divided by some area. So meaning like a sheet. It needs to be a two-dimensional object. And then volume charge distribution, rho, is equal to some charge distributed throughout a volume. Okay, a volume. Okay, that is the formulas for the denote how we denote them. Okay, lambda, sigma, and rho. Okay, and the formula we just used in the previous problem only works for sheets, two-dimensional. Doesn't have to be a sheet. It has to be two-dimensional, which is a sheet. Okay, so we have rho, so 50 is 5, and it's 5 centimeters from the axis of the cylinder, so the distance d is equal to 5 centimeters, which is just 5,05 meters. Okay, they want the magnitude of the electric field 5 centimeters away from the axis of the cylinder. Let's say I'm looking at this formula. Remember, this is a non-conducting sphere. Uh, sorry, not a sphere, a cylinder. Now the electric field inside this thing has a radius of, this is the sphere, okay? This is the, sorry, the cylinder. I keep saying sphere. This is the cylinder, okay? This cylinder has a radius of 12 centimeters, okay? But we want the electric field 5 centimeters inside. Okay, we want it at 5 centimeters. What is the electric field at a point 5 centimeters from the axis? Okay, what is the electric field 5 centimeters from the axis? The way you work that out is the electric field is equal to rho multiplied by that distance that it is away from. This will only work for a cylinder, by the way, divided by 2 times the permittivity of free space, or E naught. I just call it E naught. Okay? That's how you get the electric field at a certain distance. If you have a question, just go ahead. It's the charge density multiplied by the distance it's away from the center over 2 E naught. So, okay, let me rewrite the formula. You understand you want it inside this non-conducting sphere. The formula would then be rho multiplied by the distance it's away from the center divided by 2 E naught. So that's the formula. Now we know what rho is. Okay? Rho is equal to 5 times 10 to the negative 9. It's that 5 nanocoulomb per cubic meter. That is the volume charge density multiplied by the distance that it is away from the center, which is in this case 5, 0.05. We use meters, divided by 2 times the permittivity of free space, 8,854 times 10 to the negative 12. Okay? That will give you the electric field at a distance 5 centimeters in a non-conducting cylinder. Okay, that's approximately 14,12 nanocoulombs. Okay, remember, guys, you need to know what works for a cylinder, what works for a sphere. It does get easier because after this you'll be using just calculus. Okay, so your integrals should be on point at this point. Okay, you should be able to do them backwards and forwards. Okay, so let's go to the next problem. This is number 33. We just did 32, I think. This next problem, it's the same problem, but now we want to calculate. It's the same cylinder. Okay, it's the same cylinder, but now we want, remember, it has, we calculated it at 5 centimeters. Let's say this is the center of the cylinder. We calculate the electric field at 5. The radius of it was 12. That's 5. They now want to calculate the electric field a distance of 15 centimeters away. Okay, so R is not 5 anymore. It is now 15. It's 0.15. Okay? So how do we calculate the electric field due to a charge, an enclosed charge? Remember, this circle is now enclosing this charge. Okay, if a charge is enclosed, we use, of course, and this is how we got the previous formula. We got it from Gauss's law. Okay, you guys know Gauss's law by now. It states that the closed integral of the electric field dotted with the area vector is equal to the enclosed charge divided by E naught. Okay, Now, do we know what is happening here? Okay, so first of all, this is symmetric, so we can just say, if it is symmetric, you can just take E out as a constant, so it will be the area enclosed is equal to Q enclosed E naught. So if we work it out, by the way, you should know your electric fields, your calculus by now, integration. Uh, the area that is enclosing this uh, cylinder. Okay, what? How would I calculate the area enclosing the cylinder? Can someone hazard a guess? How would I calculate the area enclosing the cylinder? Okay, how would I calculate the area enclosing a cylinder? Okay. Anyone in the chat there? Can you write how you would calculate the area enclosing the cylinder? Remember, we can take the electric field out because it's uniform and it's a symmetric. It's symmetrically in the center. Okay, so the area, how do you calculate the area of a cylinder? The outer area, basically. The area of the cylinder enclosed by that line. The area of a cylinder would be the circumference of the circle that it makes multiplied by the length of the cylinder. Okay, that would give you the area. Because if you were to take, let's say this is a cylinder. Okay, let me just tell you something quickly. If you take a cylinder, let's say this is a cylinder. If you were to cut it open, okay, you cut it open along that line. There, you cut it right there. Okay, and you bend it flat. Okay, what will it look like? It will look like a rectangle. Okay, if you take a Coke can, okay, you cut it along one side all the way down, along one side, you cut it down all the way down along one side and you flatten it out, it will be a rectangle. Okay, so how do we get the area of a rectangle? It's length, which in this case is going to be the length of the cylinder times the width. Okay, that's how you get the width. In this case, the width of this thing, if you were to flatten it out, the width would just be the circumference. Okay, so the area of this cylinder would be the circumference, then 2 pi r, which would be the width multiplied by the length. Does that make sense? By show of hands, does that make sense? How would you get the outside area of a cylinder? It's the same as that for a uh, it's the same as that for a rectangle. Okay, in this case, only the width of this cylinder is just the circumference of the circle. Okay, then Q enclosed is still there, divided by mu naught. Okay, so this is what we have so far. It's just the electric field multiplied by 2 pi r times the length is equal to the charge enclosed over the permittivity of free space. Okay. Now, what is the charge enclosed? Okay, how do we get the charge that is enclosed in there? What is the charge enclosed? Okay, the charge enclosed, okay, is, remember charge enclosed, let me just calculate it this way rather. Let me work it out this way. Hmm. How did we get rho? How did we get rho? We took some charge, which is the charge enclosed, total charge enclosed, and we divide it by the volume of a circle. Okay, what's the volume of the circle? Okay, what's the volume of the circle? It is pi r squared. In this case, let's use r. In this case, is just a radius, so we need to use big R to denote the radius. Pi r squared times the height, which is L. Okay, pi r squared times the height. That is how we got the volume charge density. But now we want the enclosed charge again. So the charge enclosed is equal to the volume charge density multiplied by pi multiplied by the radius squared times the length. Okay, so there we have the enclosed charge. Now if we rewrite the formula that's on top, this one here, if we rewrite it, E is equal to 2 pi r L is equal to rho pi r squared times L over mu naught. Okay, this is the beauty of Gauss's law. It comes in when you need to calculate the electric field, then is equal to rho pi r squared L over 2 pi r L mu naught. Okay, we just divided by 2 pi r L. Okay, basic algebra. We can then cancel pi, we can cancel L, and that leaves us with the following formula. Electric field is equal to rho is still left, r squared is still up there, 2 mu naught or E naught rather, r. Okay, where r is that distance away from the cylinder, 15 centimeters. Okay, then we just plug everything in that we want. Okay, we know that rho is the volume charge density is 5 times 10 to the negative 9 times the radius is 0.12 or 0.12 centimeters. 2 times mu naught is 8,854 times 10 to the negative 12 times the distance away that we want is 0.5, 0.15. The distance away is 0.15. And if we work it out, approximately all of that, you work out your math. I trust you can do this on a calculator if you want to, but you get 27 newtons per coulomb. Okay. Note this, however, from our previous answer, in our previous question, we calculated that the electric field is, let me just check here. In the previous question, we calculated the electric field to be, where is it now? Is it 14? Yes, we calculated to be 14. Okay, but like here it is 27. It's because we now have the full charge, okay, contributing to the electric field. The full enclosed charge is contributing to the electric field. Don't worry, soon these type of problems is going to become normal for you to solve. If it doesn't, you are in trouble. 34. Just remember what Gauss's law says all the time. Okay, let me just check. Okay, last problem for today. A long conducting cylinder. So the cylinder is conducting. It's long. It's conducting. What is this? Can I just do this problem right now? Let me see. Yes, I just did this problem. Okay. By the way, I did not pick this one here. We did 27. If I remember correctly, the correct answer is 27. Correct. Okay, so 34. A long conducting cylinder has a radius of 6 millimeters. Okay, so which in this case is going to be 0,06 or just 6 times 10 to the negative 3 is easier. It has a non-uniform volume charge density. This is a problem usually because it's not uniform anymore. It changes the further you go out from the cylinder's axis. Where alpha, it has a non-uniform volume charge density and it's given by rho is equal to alpha times r squared, where alpha is equal to 6.2 millicoulomb per meter. That is per cubic meter, not meter 5. That is per cubic meter because it's a volume charge density. And r, oh, excuse me, sorry. It can be that because we are calculating with r squared. So yes, that is correct. And r is the distance. The actual answer will then be per meters cubed. And r is the distance from the axis of the cylinder. What's the magnitude of the electric field at a point 2 millimeters from the magnitude of the electric field at a point 2 millimeters from the axis? What's the magnitude of the electric field at a point 2 millimeters from the axis? Hint, the charge enclosed is equal to 0 to 2 millimeters. Okay, we all know that. Okay, so first of all, let's work out what is the charge enclosed. We are told that the charge enclosed is equal to 0 to 2 millimeters, 0 to r, basically, let's say 0 to r, and rho dV. Okay, that is the charge enclosed. That should be the charge has been given. That is what they told us. The charge enclosed is calculate using this formula. Okay. Now, the volume of the shell. Let's just work out some stuff. Volume of this. Uh, let's put it here. The volume of the cylinder. Okay. How do we calculate the volume of a cylinder? It is just 2 times pi times r, which is the circumference, multiplied by the length. We just did this. Okay. That is the volume, or rather that is the area, the surface area of this shell. And then we still need to multiply what? Okay, the distance from the center. Okay, the thickness, or the distance, the radius from the center. Let's call it dr. Okay, let's call it dr. It's the distance from the center. Okay, that is the volume of your charge. It's dV. Okay, I can actually write here dV, the change in the volume, because I wrote there dr. Okay, but so the infinitesimal charge then dq, the charge enclosed, therefore is then rho multiplied by dv. Okay, we know that rho is calculated with the formula alpha times r squared. They gave that to us. And then we've also now determined that dV is 2 pi r times L dr. Okay, so now there we have the formula for the charge. So now we have the formula for the charge. If we continue, the charge enclosed, remember now, it's from 0 to some r value that we want. Okay, so it goes from 0 to some r value. Okay, this is now a generalized formula. Okay, from your calculus, you will know that r would then be the endpoint. Okay, or just in general, if this is the cylinder, okay, 0 would be at the center and r would be in any direction outward from the center. Okay, we draw it here. 0 would be the center of the cylinder and r would be any direction outwards from the center. Okay, so here we have determined what is the infinitesimal charge dq. Now how do we get infinitesimal to a just Q, if we integrate dq, we will get q. Okay, so how far do we integrate it? From 0 to some sort of r. Okay, remember we are not for a specific, we're just finding the general formula. Okay, we know that rho is equal to ar squared, and we know that 2 pi r l times dr is dv. Okay, and if we integrate one side, we must, oh, that's a terrible integration sign. Your integration must be on point at this point. It must also be from 0 to r. Now, the integral for dq is just q, the charge enclosed. Now, if we were to work this out, let's work it out. We are integrating with respect to dr, okay? So alpha is a constant, it can come out. 2 pi, that's 2 alpha pi. L is also a constant. Integral from 0 to r, that is r cubed, that's 3r, r to the power 3 dr. And if you were to integrate that, that's 2 alpha pi l. That integral will become what? It will be r to the power 4 over 4. If you didn't miss your integration class, okay, that is the integral. And if we finish the integration, we get 2 alpha pi l, that is r to the power 4, the answer, divided by 4. So it's just going to be 2 divided by 4, so it's just alpha pi l r4 over 2. That, ladies and gentlemen, is the enclosed charge. Okay, that should become second nature to you. Okay, please go and practice this. If you did not understand that, it's just simple integration that I did. That's alpha, sorry. If I continue, how do we get the electric field at a certain distance? We of course use Gauss's law. Okay, and Gauss's law states that the electric field dotted with the area vector in an enclosed circuit is equal to the enclosed charge divided by the permittivity of free space. Okay, that's Gauss's law. Now we know that this is symmetrical, and then dA should be the same as the one we had before, 2 pi RL. I've already explained in a previous problem how do we get 2 pi RL. The area, the surface area, would just be the circumference multiplied by the length. The enclosed charge we just worked out is equal to pi alpha, I wrote alpha first, but anyway, L R4 to epsilon. Okay, that is, epsilon is still there. So, this is the formula. If we divide on both sides by 2 pi RL to get electric field alone, we have pi alpha L R4 2 pi naught 2 pi R L. Okay? L's cancel. Uh, there is a R there. Takes one of the R's away, so it becomes 3. Alpha's not there. There's 4. Pi's cancel. So we're left with alpha R3 on top. On the bottom, it's 4 E naught. Okay, and that is your electric field at any distance r. Okay, at any distance r, you then just plug in the values And the value for R you want. We want the electric field at a distance. We want the electric field at a distance 2 millimeters from the axis. 2 millimeters. So if we plug in R is equal to 2, we should get everything. Alpha we've been given as 6.2, 6.2, but it is millicoulomb. Okay, so it's 6.2 times 10 to the negative 3 multiplied by R3, R3, in this case R is equal to, from what we've been given, R in this case, or what they ask, is 2 millimeters away, so it's 2 times 10 to the negative 3, that is 4, multiplied by E naught is 8,854 times 10 to the negative 12. And that, ladies and gentlemen, should give you your answer for the electric field in this conducting sphere. Okay? And if you work it out, at the end, your answer will be, if you plug everything in, it's approximately 1.4. 1.4 newtons per coulomb. That is the electric field. Okay, let's see. There's an option for 1.4. It should be 1.4 something, and they round it off to 1.5. Let's check. And yes, 1.5 is correct. Okay, depends on where you round off. Now, that is all that we have time for today. If you have any questions, please ask now before I stop sharing my screen. Otherwise, enjoy the rest of your day and good luck in your physics classes and all of your other classes. Okay. Please note if you do not understand anything, please ask me. But the last problem we did, it is just your integral calculus. That I cannot teach you again. You need to go and study up on your calculus. And then it's just basic algebra for that. Okay. I'm going to stop sharing now. If you have any questions, please ask. Any questions at all, you need to ask. If there's none, then you can leave. Okay, have a good rest of your day. All the best.